Thank you very much for the introduction, and thank you very much for inviting me. So my name is Olivier. I'm a software engineer at Inria, Inria Saclay. I've been a contributor and maintainer of the part of the maintainer team of the Scikit-learn machine learning library for more than 10 years already. And 7 of those years, the last 7 years at Inria. Actually, more recently, the maintenance of the Scikit-learn project at Inria is being supported by several partners from private and public institutions. So thank you very much to them because it's very important for the long-term sustainability of the project. And beyond those, there are also other Scikit-learn core developers that have been supported for years outside of Inria. So it's not just Inria. So in this presentation, I would like to talk about open source collaboration in general. So initially, I wanted to focus more about the maintenance of the Scikit-learn project itself. But then I changed my mind a bit, and I decided to make it more like a personal story, to try to highlight the value of long-term cross contributions between different open source projects. So not just to focus on scikit-learn maintenance, but more on a typical example of the collaborations between different open source projects on a specific example. So I hope that you hear me well. There is a bit of an echo in the background, so I think if you can check that you're all muted. Okay, I will resume. So this story started in October 2017. At the time, I was working on trying to make scikit-learn to plug scikit-learn with a distributed computation infrastructure called Dask. It's also a Python project to make some machine learning pipeline run on several machines on a cluster. So several Python processes. Okay. Sorry, I have sound in my background.
As far as I can see, everybody is on mute and we can hear you very clearly.
I have big echo. Let me, I think maybe it's because I'm connected to the Gathertown. Okay.
Could it be feedback?
Yes, I had a feedback, but I think it's maybe because it was broadcasted on Gathertown at the same time.
Yeah.
Okay, that was it. Okay, so I closed it and it's fine now. Okay, sorry for that. So yeah, so at the time I was working on Dask, trying to use Dask to distribute a pipeline over several machines with different Python processes. But as soon as I started to run this kind of experiment, I went into a trouble. I got some troubles because I had a random Python process that was randomly restarting, and that would prevent my machine learning pipeline to complete. So I started to investigate and first to look at the issue tracker of the Dask project itself on GitHub, and then found someone who had described pretty much exactly the same problem that I did, and also started to analyze the cause of the problem, which was basically one of the workers or several workers would use too much RAM, and then the cluster manager would restart those workers to avoid exhausting the memory, but then that would prevent the completion of the job. So I went into the source code of Dask and found that the way the memory was managed on the workers was not necessarily optimal. And so I started to optimize the garbage collection process whenever there was a high memory event on the workers, and I could fix some of those bugs. And this was integrated in Dask quite quickly. But it was still not fixing completely my problem, because I still had the issue, but on more rare occasions. And after that, I could not find any other problem in Dask itself. So the problem was actually caused by dependencies of Dask. So if you consider the packages that I was using for this experiment, I was using a Dask data frame. So it's a Dask distributed data frame that is built on top of pandas, that is itself using NumPy for the memory allocation of the columns of the pandas data frame. And whenever you ship Dask ships chunks of data between workers on the clusters, it's relying on the CPython standard library, in particular on a module which is called pickle, to handle the serialization of the NumPy arrays. And actually, Dask can also use an extension of that pickle module from the standard library. To be able to serialize a dynamically defined Python object, the classes and functions and stuff like that, that are defined in a Jupyter session when you do interactive development. So those are the main projects that are involved in this bug. So I started to investigate and found the root cause was that under high memory pressure, when the workers are working really hard on large chunks of data, Dask starts to dump intermediate object to disk to release some memory. To free some memory, intermediate data buffers are dumped onto the hard drive of the workers to make sure that we have enough memory to process the things that is really needed for the next step of the pipeline. However, in doing so, those memory buffers are based on NumPy, and NumPy, when it serializes its arrays to disk, it's actually making extra memory copies that are not needed, but those are spurious extra memory copies. And then that would trigger the memory usage of the workers to go above the limit of Dask, and then Dask will restart the workers. So this was the fundamental cause of the problem. And the reason why NumPy does this is that because the way the pickle module of the standard library of Python is written, it has no natural way to serialize and load read-write buffers without making those extra memory copies. So it's a design decision in the CPython standard library that was preventing NumPy to do something more efficient here. And furthermore, even for read-only buffers, so NumPy is read-write, but even for simple read-only buffers, the pickle module was not optimal and was doing those extra memory copies. So that was unfortunate. And so I started to look into the simple use case of read-only buffer. So not NumPy, just pure Python memory buffer in read-only mode. So this was already in December 2017. So 2 months after my initial tentative to use Dask. And at the time, I had a look at the source code of Python standard library in the pickle module, which is written in C. It was the first time that I read this kind of C API for Python. And I found quickly the root cause of the problem, and it was actually possible to fix it without changing the specification of the pickle protocol. So I started to submit pull request reviews, and that got very nice pull request. I sent the pull request, and I started to receive very nice reviews from Antoine Pitrou and Cyril Storchaka. And during the process, I educated myself because they were very nice with me as a first-time contributor, and that was very helpful. And so soon after that, we could fix it, and this was merged and accepted in CPython. So we would have to wait for the new version of Python to be released to actually benefit from the fix, but at least it was fixed. But then this was only fixing the problem for just pure Python object, and I still had my problem with Dask and NumPy and so on all together. So, and furthermore, I would have to wait for Python to be released to benefit from the fix. But because I was also a contributor on Cloud Pickle, I knew this module quite well, and I knew that I had more flexibility in this module to actually fix the problem for NumPy. So I started to do this, and then found a series of hacks that could make it possible to work around the design limitation of the pickle module in the standard library. So I started to do this, to write this kind of code to introspect if a Python object is being referenced by other Python objects, to know whether or not it's safe to convert a read-only buffer into a read-write buffer without causing bugs for third-party users of the same buffer, like to make sure that there are no other reference to pointing to it. So it's kind of low-level hacky things because I need to directly access the memory address of the buffer and to wrap it again into an NumPy array. And also I had to deal with the case because we were supporting all versions of Python, so that had their own bugs that I had to work around to avoid the problems with the garbage collector. So it was kind of complex and very low level and kind of tricky, and it was a series of workarounds that are not really natural. But in the end, it worked. And so I submitted the pull request to Cloud Pickle, and then I had a review by another Cloud Pickle developer who found it really impressive work. So at the time, I was very, very happy with myself, very proud, and the two of us were enjoying a very low-level hack that would fix my problem. But then I just waited and decided not to press the merge button because I had in the back of my head the feeling that it was too much of a hack and that maybe it was not a good idea to accumulate this kind of low-level hack that few people would be able to understand in the future to maintain this project and the projects like Dask that are built upon it. And it's just not just Dask, actually. It's also used by Ray, by PySpark, and many other cluster computing things in Python. So I was not very comfortable in merging this. So I decided to wait a bit, thinking that there might be a better way. And in the background, actually a bit later, in March 2018, Antoine Pitrou, who is the Python core developer who reviewed my initial pull request for the fix for the read-only case, understood better based on that experience that the pickle protocol was really the specification of the pickle protocol was really a limitation here, a fundamental limitations, and that it should be lifted. And so he proposed a new extension of the pickle protocol, a new specification, to make it possible to support read-write buffers without memory copies much more efficiently. So this is a new design spec, so it takes time for the C Python core developers to review it and to assess whether it's too complex to maintain, if it's worth it, if it's actually useful for users, and so on. And so to accelerate this process, in parallel to the specification itself, Antoine provided a backward compatible implementation for previous versions of Python, Python 3.6 and 3.7, so that other people could start to experiment with this fix. And so in May 2018, I went back and discovered this, and I said, oh, maybe I can fix my original problem cleanly this way. But then I need to make NumPy leverage this new way to serialize the read-write buffers efficiently without memory copies. And so I needed to upgrade NumPy basically to use this new version of CPython to work with this. So I submitted an issue to NumPy with a minimal proof of concept Python implementation to show that you could actually remove the memory copies, and did some benchmark and evaluation to show that it's actually working. But I just did the pure Python proof of concept instead of actually fixing NumPy, because the NumPy code was written in low-level C. And at the time, I was not very familiar with it, and I did not have time to actually work on that because I was also working on other stuff. And hoping that NumPy core developers will pick it up from there, But unfortunately, we're also busy on other things, and my issue kind of stays stalled basically for a couple of months. But later, in September 2018, we hired in the meantime another engineer in our team at Inria, Pierre Glaser, to help us work on low-level things like this to make Scikit-learn work more efficiently in general, and also to work on upstream matters that I didn't have time to fix myself. And so Pierre started to resume the work and actually submitted a full pull request to NumPy with the full fix plus benchmarks and so on. And then we received reviews from NumPy core developers, Matti Picus and Tyler Reddy, and also Antoine Pitrou from the CPython core developer team also reviewed the pull request, and we were quite happy it was working. And that was also a good use case to motivate the fact that the new specification of this protocol was actually useful for very important projects such as NumPy. So that would help us move the case forward in CPython itself to get the PEP accepted. Maybe I was a bit quick, but PEP here means a Python enhancement proposal. It's whenever the core developer of Python wants to make a big change in the standard library or in the interpreter, or in the language definition itself, they write a document to actually document the change, the motivation, the purpose, the different solutions before actually writing a pull request. So to be able to discuss the design before actually focusing on the implementation. So after that, I was really happy to see that Antoine Pitrou also contributed to other projects such as Apache Arrow, which is a shared data structure for many big data open source projects in the Java world, in C++, in Python, in R. So he could actually make the Arrow project very efficiently pickleable using this new extension of the pickle protocol. And what was funny to see here is that Wes McKinney, who is the initiator, one of the initiator of the Apache Arrow project, and was also the initiator of the Pandas project in Python for the DataFrames, said that the copying of memory in unpickling of NumPy arrays was a problem that he had identified a long time ago when he was working in Pandas, like 10 years ago. And at the time, probably didn't have the time to correctly fix it, but was very happy that someone would do the job. So it's interesting to see that those kind of low-level issues might be impacting many people for a long time, but maybe did not have time to go upstream and to make that effort to talk to the upstream contributors and maintainers to actually fix the low-level root cause. So moving forward in time, in June 2018, 19, then finally the specification was accepted in CPython, and the implementation was accepted in CPython, and later was released, and so we fixed my actual original bug 2 years later. But actually we fixed it on the full stack and not just using a hack on one single project. So we fixed the bug for many other use cases and not just my initial use case. So is this the end of my story? Actually, no, because meanwhile, in February 2019, so moving back 6 months earlier, or 5 months earlier, Pierre Glaser, since he had the opportunity to work with me on fixing this, improving low-level pickle stuff in NumPy, then he was more confident about low-level pickle stuff in Python, and at the time we were also working together on multi-process computation on a single machine using a component that we wrote, which is called Loki. And this is actually what is used in Scikit-learn when you do a parallel computation on a single machine by default. And this component is also using Cloud Pickle to ship Python objects that are possibly interactively defined between different Python processes. And the problem is that with Cloud Pickle, this is written in pure Python, and it's inheriting from the base pickler class, which is also written in pure Python in CPython, in the standard library. The problem with this is that the Python implementation is very flexible and makes it possible to actually implement what we need in Cloud Pickle for interactive class definitions and so on. However, it's very slow because it's written in pure Python. And in the standard library, there is also a C implementation of the same pickle protocol, but you cannot really benefit from the same flexibility. So we cannot directly derive from the C implementation in Cloud Pickle to customize it and to extend it. At least that was what was the case at the time. And because of that, we were suffering for high CPU usage where we ship Python objects between the workers, and that would slow down the processing and make this very suboptimal from a performance point of view. So we fixed the first memory usage problem, but then we had a high CPU usage problem that we could optimize further. And so because we had this experience with the low-level interaction, we decided to embark on trying to talk to the CPython core developer to see if we could not make it change the implementation to make it much more efficient from a CPU point of view. So we started to open a new pull request. So actually, Pierre wrote most of it. And actually, we started with some discussions, and then once we a first design, we submitted the pull request. And it evolved. We received the feedback from Antoine Pitrou again and other core developers, and we could finally extend the CPython implementation of the C implementation of the pickle protocol in Python, so to make it such that in Cloud Pickle we could benefit from it. And that was quite quickly accepted and merged. Actually, not that quickly because we refined the design a couple of times based on the feedback of Antoine Pitrou. And actually, we had to do 2 pull requests in 2 different corners of the standard library to make it work. But then finally, in October 2019, Python 3.8 was out with the pull request. And then we had a very efficient Cloud Pickle that would be both efficient from a CPU point of view, and the full stack would be very efficient at shipping objects from a memory point of view without making extra memory copies all around the place that could cause cluster computation to crash randomly. So this is the end of my story, and the conclusion of this is that open source is really not a zero-sum game. When you have this kind of interactions between open source developers of different projects, the effort that they invest can be sometimes multiplicative rather than additive, and especially those kind of investments, you make them by investing time in making careful code reviews and helpful code reviews where you educate one another. And by doing so, you see that the quality of the contributions and the quality of the understanding of the problem is improving very efficiently over time. And so it's an investment in the shared understanding both of the technical aspect of the code, but also of the end user needs. In this specific case, the original writers of the pickle protocol in CPython did not anticipate that this will be a fundamental building block for interactively shipping a Python object on data science clusters. And so they did not really care about the extra memory copies because they did not anticipate that there could be multiple gigabytes of chunks of data going around on a cluster, and that those extra copies could trigger the worker to fail and so on. And so by doing these investigations and by talking to the different open source maintainers, we built this shared understanding of the actual user needs of Python in a data science setting in a high performance computing environment. And furthermore, investing this time in code reviews make it possible to build some trust between the core developers of the different projects, and we could work more efficiently over time. So I would like to thank everyone who was involved in those few pull requests. So Pierre working at Inria with myself. Now he has moved on to do a PhD, but he's still working on the same project. Joey and Matthew working on the Dask, Cloud Pickle, and so on. The CPython core developer team who was involved in those pull requests, like Antoine, Seri, Victor, and Terry, and some NumPy core developer who reviewed the pull request on the memory, the pickling for NumPy. And Antoine is also involved in all of them, all of those projects. And so as a funny side note, as a result of this experience, so Pierre had the opportunity to contribute to CPython and NumPy because of this. And then GitHub, a few years later, gave us this kind of achievement badge, because this code in CPython and NumPy was actually used for the Mars 2020 helicopter mission at the NASA, and they had a disagreement with with GitHub to reward with the badge all the open source contributors to the projects that have been used by the Mars 2020 helicopter team. And Python and NumPy were obviously a major component of that scientific project. So it's actually nice to get this kind of feedback, that the work that the effort that we put into improving the maintainability of those projects is actually used for the wider scientific progress. So finally, I would like to highlight that the value of those open source collaborations, those long-term open source collaborations. I say long-term because if you remember, my original bug report started in 2017, and the release of Python and NumPy and all those projects with the full fix of the original problem. Because of the release cycles and the iterations and so on, it was the end of 2019. So it took more than 2 years to fix the root cause of the bug in the full scientific Python stack. But this long-term value is only possible because we are privileged at Inria to have received long-term support to actually work on those problems. In particular, Inria has been supporting me for many years, but as I said previously, other open source developers are also supported by private companies to work on this, and in particular, the Inria team is supported by those partners. And this is really important because it gives us the flexibility and the confidence that we can spend a couple of months or even years to work with upstream projects to fix the root cause of those problems. Because if I was just an open source volunteer contributors working on my spare time during the weekends on Scikit-learn, probably that I would just focus on the low-hanging fruit in Scikit-learn, and not spend the time to investigate in finding the root cause and understanding the code of the upstream open source project. And this is only possible because we have this kind of privilege to be supported to work on open source on the long term. So thank you again for all those partners, and thank you very much for your attention, and hopefully see you later on GitHub. So now I think we have a bit of time for discussions and questions. And if you are interested, we can exchange a bit more about maintenance issues of Scikit-learn. I have a couple of ideas of a couple of questions that we could talk about. What it means that code is evolving, and in particular discuss the fact that the dependencies of a project are always evolving, and even the hardware is evolving, and what can we do to make sure that the code is maintainable and maintained and useful and valuable over time, given those constraints. We can also talk about the fact that code is only useful if it's installable on end user platforms, and the importance of continuous integration, continuous delivery to build working packages for many different kinds of architectures. And also the fact that code is valuable if it's readable. It's not just write once and execute. Is something that you have to read over and over again to build a community of contributors that are confident that they can make it work and make it evolve the way they want. And talk about the importance of consistent and explicit naming, the kind of documentation strategies and quality enforcement that we do in Scikit-learn, the kind of comments that we do, how we deal with code styles, so this was more anecdotal and so on. So yeah, feel free to ask questions. And actually, there are already questions in the chat, I think. So maybe I can start with this one. So I will read it out loud. So the question is, how did you solve the memory fragmentation issues when dealing with multiple chunks of sequential data between different processes? Was it handled by CPython memory management? So it's a kind of a technical question about the original problem. Maybe I can use this slide. So actually, when in this problem, in this pipeline, I was using Dask distributed, and in particular the data frame construct of Dask distributed. So the data frame of Dask is a logical view on physical data frames that that are basically chunks of the full data frame that actually live in the memory of the different Python workers. And those chunks are actually regular pandas data frames. So a Dask data frame is just a collection of small pandas data frames, and each of those small pandas data frame actually live in memory on the worker nodes of the Dask cluster. And the actual memory allocation of those of the columns of those Dask data frames, of those pandas data frames, are actually regular NumPy arrays. And those NumPy arrays are contiguous blocks of memory. So they are contiguous in memory. So the problem that I solved was actually just about serializing continuous chunks of data. So it was kind of easy. It's just a single memory buffer that I was processing at a time in the pickle module. So both for read and write. Okay. So each of those chunks is typically a couple of hundreds of megabytes or gigabytes, or a couple of gigabytes. And the actual size of the chunks, you can control it when you use Dask. As the user, you can say how you want to repartition your Dask data frame, and you can control the size of the chunks. Okay. So if you have other questions.
I didn't want to interrupt, Olivier,
Yes.
but I would like to thank you very much for your talk. I think this was incredible, very, very valuable insights, I think. And thank you so much for giving us and sharing like these insights. I think it's very valuable for a lot of open source contributors out there. And I think the takeaway for me, I very much liked it when you said the kind of bottom line is to invest in a shared understanding of code, but at the same time to understand end user needs and trust. I think that's very important. And secondly, yeah, as you said, it took like 2 years or more than 2 years for your initial bug to get or to be fixed. And I was just wondering, like, what is how to strike that balance, or how to know like what to do, or how to contribute, like understanding that you have to have this long-term value or long-term mindset when thinking about open source, especially like when you're fixing bugs, for instance, that are very low level where you have to go to the root cause of something, versus, as you mentioned, like the open source contributors that might contribute in their spare time on the weekends, and maybe after looking more after low-hanging fruit. How would you strike that balance? When would you know how to contribute?
Yes, so that's a very good question, and I think there is no easy answer to this one. So it really depends if you have the physical opportunity or the privileges to invest in the long term. So sometimes you just do not have time to fix all the open source problems in the world. So you have to find an easy fix, a workaround, and live with it. But at least what I think is important is at least to document in an issue all the investigation work that you did to build the understanding, to build the workaround, and to open the issue on the upstream project, to inform the upstream maintainers that you face this problem. You do not have time to correctly fix it upstream, but here is what you understood and how it's impacting you, and also mention that you found a workaround and that your specific users are okay. But that on the long term, it would be very nice if someone could tackle the original root cause. So I think that would be the minimum. And also if you are in a production setting, sometimes you cannot just wait 2 years. Here in my case, I was just doing a benchmark pipeline, so I had no like very important constraints. I could just to solve my initial problem, I could just like refactor a bit my pipeline and do not run into that problem, and move on working on Scikit-learn, for instance. And also, I could also take the intermediate step to find this workaround that I talked about at the beginning, that the series of hacks that I did in Cloud Pickle, that would have been enough, and it just took me a couple of days to fix the problem for my pipeline. And if I had been working, for instance, in a startup, and we needed to ship a product very quickly, that would probably be the solution that I would use. Like I knew that I could maintain that for instance, for my hypothetical startup, and that would be very efficient from a performance point of view to solve the original problem. But that would not have solved the problem for the wider open source community. So I think it's fine to come up with workarounds and to maintain them in your own local code base. But it's important to document the root cause of the problem so that the original open source contributors at least have the opportunity to understand that there is a problem and that there are possible fixes, even if they are complex to deploy and to implement and to deploy. So there are other questions. So this questions and comments. How do you communicate among the main maintainers of Scikit-learn, given you all work in various places? Is it through GitHub and pull request issues mostly? So yes, that's an interesting question. And the answer has evolved a bit over time. Initially, when the project was small, it was very Inria focused for the first couple of months, I would say, of the project life. So people would interact directly, and just at the time we were using Subversion and SourceForge. So there were just a couple of issues, but not much, and was mostly either in direct meetings or on the mailing list, on the public mailing list. But then very quickly we migrated to GitHub, and that was very the way the GitHub user interface is organized makes it a very nice communication tool. And so it's very nice to use pull requests and issues to have a focused technical discussions on one specific focus at a time, topic at a time. And so I think this is from a bandwidth point of view, I think it's like where 99% of the communication happen, which is very useful because it's very efficient and we can resolve problems this way. And solve and move forward with individual issues. Sometimes it's not enough to get the big picture of the project or how the project is moving. And to get this big picture, initially we used a bit the mailing list, but the user experience with mailing list is not optimal, I would say, or at least not all people find it optimal. And so we have additional communication channels. So one thing that we started to do recently is to have monthly meeting using video call. Well, it's not working. This is not, yes. I still cannot spell Scikit-learn after all those years. Okay. So we started to have a monthly meeting once a month using video conference calls. for the core developers, but they are open, so anybody can attend and join and even discuss their topic. We try to keep them to 1 hour long per month, and usually we go a bit over, but and we have a collaborative editing agenda note-taking system, so that we have the notes of the meeting that are also published later. And on top of this, so this is those meetings are actually useful for coordination and maybe to help us refocus on the long-term effort for the project. Like we know that there are some refactoring in the scikit-learn code base that are taking many pull requests and they are spending many years. And sometimes we lose track of those, and using those meetings we can re-emphasize that we need to finalize those pull requests because they are important for the long term. And we also have additional communication channels that are mentioned in the README. So we use Twitter for announcements. We use Gitter for interactive discussions from time to time. And Gitter is especially useful to coordinate the effort between when we are releasing a new version of scikit-learn, because most of the time when we freeze the code base for a release, it usually takes a couple of weeks to fix all the blocking issues that we need to have merged before being able to actually release, like fix the build for this particular architecture that has been failing for 2 weeks and nobody had the time to fix it. And so, and to coordinate the effort between, I would say, 5 to 10 developers on a subset of 20 issues that are really high priority to unblock the release, I would say. We also use Stack Overflow mostly to support users, and also GitHub discussions more recently, which is, I can show you in the user interface. It's a new tab in the GitHub UX, where it's actually not a real issue tracking. It's more like to ask user questions. And sometimes there are more like methodological questions on how to use scikit-learn to solve this particular statistic problem, for instance. And maybe it's not about a specific issue in scikit-learn, but more about how to use it. So it's kind of useful. It's quite active, but yeah, it's kind of picking up. It's quite new. And yeah, I think that's it. I would say. Do you have other questions? Nope.
Awesome. Thank you so much, Olivier. This was fantastic. If we don't have any other questions, or do we have any last questions? Let's give it another shot before we close.
Yeah, maybe I think there is an interesting difference between big science, where big science has a lot of researchers. So we were thinking a lot about what make a researcher interested in participating in your project, right? And I think scikit-learn is more about engineers and people who really like more like who are more tech focused. And I was wondering what kind of made you excited about joining the project in the beginning, and what kind of what you think makes somebody excited to participate in the project over the long term, I would say, to stay a few months. Yeah,
that's interesting question also, and the answer is evolving over time. When I started scikit-learn, joining the scikit-learn team, I was doing that as a volunteer on my spare time. And initially, the project was probably more interesting to contribute to at the beginning because it was completely new. So we had to write all those machine learning implementations for many different kinds of methods. And it was actually writing a lot of new code, and so it's always more fun to write new code than to maintain older code, even though it can be often also to dig the root cause of a problem. But yeah, so at least I think it was easier to contribute to scikit-learn at the beginning, at the time where we were few of us and the code base was much smaller. But why I found it really interesting to stick around in this project the two motivations. First is that by reviewing others people pull requests, I started to learn a lot about various topics on machine learning that I would never have the opportunity to learn about otherwise. So I started to develop this kind of a broad expertise of many different subfields of machine learning, just because I had to review a pull request, and so I had to read the papers to know about what this method was actually doing on support vector machine, Gaussian process, and every different kind of things, and so and started to and all of this. I think my main motivation, my main personal motivation to work on Scikit-learn was to learn new things over time. And then the other motivation is actually to see that your code is useful for many people. Like over time, the growth curve for the adoption of the project has been doubling in number of users every 2 years or something. And nowadays, I think there are 1 million monthly users on the website. So we know that there are at least 1 million data scientists who use Scikit-learn on a regular basis. So that's really like motivating to know that your work is actually useful to solve many scientific problems, even though you do not know the details. You do not know often which people are using Scikit-learn for what problem. But still it's very rewarding, I think. And but I agree that it's challenging, I would say, for new contributors to get into the code base nowadays, because it's much more complex. And when you want to change something in Scikit-learn, we are much more conservative than at the beginning. And so we don't want to break our user code by changing a public API or something like this, or even the behavior of a model. We try to be conservative and to use a deprecation cycle of 2 releases. So it means that when you change something in a model, for instance, you fix a bug that was not necessarily a bug for every users, and it's more like changing the default behavior. We want to keep the old behavior for at least 2 releases, and we do 1 release every 6 months to 1 year. So that means that for 1 year and a half, the code, the default behavior of the code will not change. And it's just you have an option to activate the new behavior, and we just have a warning message that tell the user that warning in release 1 point something, the new default will be the new default behavior will change, and if you want to preserve the whole behavior, use this flag, or if you want to directly enable the new behavior, use this flag. And this is very important to not break the user and the adoption, and to not cause frictions for users. But at the same time, it's causing a lot of friction because it's imposing a lot of complexity, of software engineering complexity, to deal with those deprecation cycles for first-time contributors who are just focused on the mathematical idea and do not necessarily want to care about this technical details of software engineering maintenance. So yeah, but it's a trade-off. There is no good solution. I think we have to deal with this trade-off.